It's 11:11. Good morning, everybody, and welcome. Hopefully everything went well last night. You had a good sleep and you're ready for the rest of the semester. Not too much left. We got a couple of chapters to do. Chapter 10 on oscillations and simple harmonic motion. Chapter 11 on waves, and then that's it. Today I'm finishing chapter 9, actually. We're going to do a soup race. It'll be chicken broth versus cream of mushroom, and we're going to see who wins. A couple of questions on the pre-course survey about the final exam, like how many questions are going to be. It's a bit longer than a term test and worth a bit more than a term test, but it's 2 hours. So there'll be 2 of the long answer questions. One of them will be from this chapter 10, because that's what we're going to be doing next week. Actually, is practicing writing out chapter 10 problems for the mock quiz. But it's a cumulative final exam, chapter 1 through 11. We do the whole course. It's pretty evenly spread otherwise. Okay, last time I was going to ask you about this figure skater. So we know, and we actually saw this when I was on the rotating chair, is that if you start off with some initial rotation, rotational velocity omega, and then you change it, change I, then you'll also change omega. So the way it looks is you've got, I guess, L initial equals L final. That's sort of your equation. And so L initial is equal to I initial times omega initial, and L final is equal to I final times omega final. So it looks like I initial, omega initial equals I final, omega final, right? That's kind of your equation, conservation of angular momentum. And then the other equation that you'll need somewhere here is that the kinetic energy is equal to 1/2 I times omega squared. So I want you to think about that. I don't think this is entirely obvious, but think about it. Pair up. Share your answer. It should be either kinetic energy goes up or down or stays the same. Larger. Okay, well, I think that actually does work out. I put it as green. I'm a little bit wondering where the energy comes from. But yeah, I think that's right, is that I goes down. And omega goes up. I think if you solve out this equation, it's something like omega final is equal to I initial divided by I final times omega initial. Something like that, right? So what that means is that it's an inverse ratio. So what I think is that omega squared goes up more because it's squared. So you'd think they'd cancel out, so the same might be right, but I think it's actually larger. So I've been wondering about this, but I think what's happening is that, for example, with me holding those 5 kilogram masses, I feel like I had to apply a force inward in order to pull them inward, because I was feeling them getting pulled outwards in my frame of reference, right? So it took me, I had to fight that centrifugal force and pull them in, and that's doing work. Okay, force times a displacement. The force and the displacement are in the same direction for both those 5 kilogram masses. So I'm clearly doing work on something. So that, I guess it's me, the system, and so that's why we end up with more rotational kinetic energy. That's how the energy balance goes, I think. And it's the same with the figure skater. She's doing some work to pull her arms in, and that's giving her the more kinetic energy. I mean, it's all internal forces, but I guess what's happening is chemical energy in her muscles is being changed into the kinetic energy of the spin. So good job. Okay, I think I didn't do this one last time. Let's do this. You got a 5.5 kilogram basketball rolling at 1 meters per second. What's the kinetic energy? So it seems pretty straightforward. They tell you here that the rotational inertia of a hollow sphere is I equals 2/3 mr squared. That's coming from that table 9.3, and it's the kind of thing that I would give you actually on the test. I'm not asking you to put table 9.3 equations on your 8 sheet. But basically, it looks like this. You've got basketball, and it's rolling. And so it's got V is 1.0 meters per second. That's the linear speed. It's got some radius R. It's got a mass, 0.5 kilograms. And it's rolling without slipping. So when things are rolling without slipping, you have these other equations. And the main one here is that V is equal to omega times R. So omega is equal to V over R. So that means that the whole thing is rotating. Well, it's clockwise there, but you get it, right? It's something like that. Looks like it would be actually negative. But anyway, the point being that kinetic is equal to the kinetic translational plus the kinetic rotation. So we're going to model this as being something, a center of mass that's moving along at 1 meters per second. Come on in, grab a seat. Looking for your wallet? Uh-oh. People could look right. Where were you sitting? There's no wallet up here. I'm just in the middle of teaching a physics class, so I'm going to go back to this. Good luck. So it's 1/2 m times v squared plus 1/2 I times omega squared. Those should be from your age sheet. So I got 1/2, and then you have to plug in a bunch of stuff. The mv squared is easy. Plus 1/2 times the 2/3 mass times r squared. That's I. Times v over r squared. So now you can kind of, well, I can square, there's a v squared over r squared. There's a 2 over 2 times 3 is 6. And there's an m and there's an r squared. So you have to simplify this stuff a little bit, but it's interesting, it sort of works out to be the kinetic energy is equal to, well, it's equal to 1/2 mv squared plus 2/6 mv squared, because these r squareds cancel. So you can just do common denominator 6, so 3 over 6 plus 2 over 6 is 5 over 6, I guess, times mv squared. So we get 5 over 6. That's for a rolling hollow sphere. It's 5/6 mv squared is the total kinetic energy. 5 over 6 times each times 1, or sorry, 0.5 times 1 squared. So I got 0.42 joules. Okay. Okay. So, and then I want to go over a little bit, last time we had the solid hoop versus the hoop versus the solid disc, hollow hoop, I guess, and the solid disc tends to win. So this is sort of what we did. Solid disc wins, but why? So I want to go through this twice. First, I want to just do the sliding without rolling case. Pretty easy. What is the acceleration of a sliding object down a ramp at an angle of theta? So the sketch looks something like this. We use the block or something. What we do is we define y to be, you tilt your axes. So y is perpendicular to that surface, x is along the motion. The force diagram looks like this. You've got N, you've got mg. Don't forget to now divide your mg. This is going to be fg, negative fgy, and you got fgx. Oops. Yeah. X. So it's a sub x is equal to the sum of all the forces in the x direction divided by the mass. So that's just going to be mg sine theta, I think, divided by m. So a sub x is equal to g sine theta. That's kind of chapter 4 or something like that. So, okay, so that's kind of our reference. If there was no friction at all, then any object would just slide without rolling at g sine theta. So now we got to add some friction, and we got to add some torques and all this stuff. So it's going to get a little more difficult. It's a rotational dynamics kind of chapter 9 problem. What is the acceleration of a round object rolling down a hill inclined at an angle theta? Assume rolling without skidding or slipping or whatever. So now we got to draw it a little more carefully, but it's the same basic idea. Here's an angle theta. Here's the round object. I think we'll maybe define the axis to be in the middle, axis, around which we're going to compute torques. I can still tilt my axes, so x is down the hill and y is up the hill. We'll call the radius is capital R. The mass we'll just define it to be m. And what I'm going to do is I'm going to set rotational inertia, because it's not given. So let's just say that it's I equals something times mr squared. It's always something, right? And it's dimensionless. So let's call it x times mr squared. And we can fill in x later when we look up that table 9.3. It could be 2/3 if it happens to be a basketball, or it could be 2/5 for a bowling ball, or half if it's a solid disc like this. We'll just fill it in at the end. But this way we'll get a nice, useful general answer. For any time you got a round object, you can put this one on your A sheet. Find x from table 9.3. So I think ax is positive, the way we've set this up, plus x direction. And alpha is, the whole thing's rotating this way, and it's speeding up. So I think that actually, if that's the direction, alpha is negative, I think, for it's not clockwise acceleration, right? Clockwise angular acceleration. So I'm going to use this equation that alpha is equal to negative a sub x divided by r, just to keep track of my signs there. And so let's draw a force diagram. It kind of looks like, let's just draw it here. What are the forces? Well, we'll draw them in red. Certainly there's gravity, which goes on the center of mass, which is at the center. So we'll call that mg. Then there's going to be kind of this normal force going from the surface towards, like perpendicular to the surface, and I think that goes through the axis. So I think the lucky thing about the normal force in this case is that it doesn't have any torque, because that force line passes through the rotation axis as I've defined it. So the torque is coming from, and also the gravity doesn't have any torque. All the torque is coming from F sub s, the static friction. So I'll just make a note here that if the center is the rotation axis, then that implies that the lever arm for N and mg are 0. And in any case, there's no torque from gravity or from the normal force. So this means that only F sub s provides torque. And also, F sub s is in the negative x direction. So it's going to slow down the a acceleration. But there's also a component of mg in the plus x direction, which I guess is going to be hopefully greater to accelerate this whole thing of mg in plus x. So that's the reason the thing goes down the hill is because that mg sine theta is bigger than the static friction going backwards up the hill. And the static friction is there to keep the thing rolling without slipping. So we're going to let's do first Newton's second law, just the old one, which is that the sum of all the forces in the x direction equals m times a sub x. But now we've got mg sine theta minus fs. And fs is a self-adjusting force. We don't have any idea what it is. It's just something. So we'll write it down, and you get max. It's an unknown. We'll call this equation 2. A little box around it. And then the other thing, also, the Newton's second law for rotation is that the sum of all the torques is equal to I times alpha. So that's just negative F sub s times R, because the friction is clockwise direction. And the lever arm here is R, from here to here. And that equals xmr squared times alpha. And that's your third equation. You've got 3 equations and 3 unknowns. You solve it all out. You just get 3 equations. The 3 unknowns here are you don't know static friction, you don't know alpha, and you don't know a sub x. But we're trying to find a sub x. So eliminate f sub s and alpha and solve for a sub x. That's what I would do. So first let's plug 1 into 3. I got negative fsr is equal to xmr squared times negative a sub x divided by r. And then I think I can divide both sides by r. So this r squared and this r go away. And then I could also the negatives cancel out, so I just get f sub s is equal to x times m times a sub x. Oops. This r goes away. So this r canceled this squared, and this r canceled that r. Anyway, hopefully you get it. Okay. I think I'm right. And then what you do is we'll plug this into 2. Into equation 2. And I get mg sine theta minus x times a sub x equals m times a sub x, and you just solve it out. So I think there's m's in every single term there. Divide both sides by m. And then what else? I end up with g sine theta minus x a sub x equals a sub x, and g sine theta equals a sub x times 1 plus x. And I get a sub x is equal to g sine theta, the old g sine theta, but all divided by 1 plus x. And that's less than g sine theta for the sliding thingy. That's because static friction is sort of countering your gravity force. So that's a handy result. Put it on the second screen here. If you know that the rotational inertia is xmr squared, and it's rolling without slipping down an incline of angle theta, then the acceleration will be g sine theta divided by 1 plus x. So, we're going to do soup in a minute. What's the acceleration of a frictionless ice cube sliding down a ramp of an angle? It's just a sub x equals g sine theta. Solid disk, well, it's going to be a is equal to g sine theta divided by 1 plus a half. think it's going to be something like 2/3, right? And then A, what about a hoop? A is going to be G sine theta divided by 1 plus 1. So this, I think, is actually equal to, this is going to be 3/2 in the bottom, divided by, so it's 2/3, G sine theta, I think. And this is going to be a half G sine theta. So this is, a half is less than 2/3. And that is why the solid disk always wins the races. And then you could do a glass marble. Well, it would be a solid disk, right? So it would be a solid sphere. So A is equal to G sine theta divided by 1 plus 2/5, I think. Sound good? All right. So next we're going to do soup. The big question here is, what is the fastest soup? So I have 2 cans of soup. One is cream of mushroom soup. So I don't know if you've ever eaten this stuff, but especially before you add water, it's very gelatinous and sticky. You could like stand a spoon up in it and turn it upside down, almost like, you know, when you order a Blizzard, they always turn it upside down. It's because it's so sticky and solid. So it's like a solid thing. But this is chicken broth. So it's much more liquidy. You can hear it kind of shaking around there. It's almost like water. So liquid versus kind of like solid. So I'm going to race them. Go on top hat. Make your prediction. Which will win? Mushroom soup is the thick paste. So when it's rolling, the contents rotate along with the can as one solid object, like a solid cylinder. And chicken broth is a low viscosity liquid, so the can itself rolls while the liquid might just kind of slide along. Please check your neighbor, see what your neighbor's voting. And then we'll try it out. Jonathan was telling me that this race is fixed. Fixed by the laws of physics, that is. Did you find that guy's wallet? No, something. Oh, okay. Let's click in a prediction, people. 10 seconds, and then we'll try it. Let's see what people... Is aux plate? Yeah, okay. The camera needs to be moved. Okay. I don't know if I've kicked it. Let's see what the prediction is. Who are you voting for? Ooh, 58% are voting for the chicken broth. 36% are voting for cream of mushroom. And only 6% say a little bit. So yeah, I don't think it's going to be, there's going to be a winner. Let's do aux plate. Yeah, we need to see the starting line. That's okay. So what I've got is chicken, the chicken broth is this one, the one in front, and the mushroom is behind. We kind of need different colored cans or something. Marks, get set, go. Okay, so this one won, and that's the chicken broth. So I can't really see it. It's too glary. Anyway, let's do it again. We'll put the mushroom soup kind of closer to you. So this is the mushroom soup. So it's weird, eh? So you were right. I think 56% of you got that one. 58%. So, and I kind of knew it was going to happen. Colored it green. What I think is going on here is the cream of mushroom soup must rotate because it's all sticky and sticking to the inner surfaces of the can. So it's like a solid disk. And I think you end up with a bunch of rotational kinetic energy. But I think that the majority of the mass of the broth doesn't probably rotate at all. It might get a little mixed up, but I think it just kind of goes along, if you can imagine that. Almost like the box, frictionless box or something. So this is going to be a lot closer to G sine theta, and this is going to be closer to half G sine theta. The chicken broth always wins is the moral of that story. How are you guys feeling about chapter 9? I think we're done with it. Good front row's good. I'm really glad to see all of you here. I don't know, you're probably noticing that there's also some empty seats. You might wonder where the hell everybody is, but I saw the same thing in bio, so I guess people are just... Is the chemistry test today? Okay, that would explain it. I'm very glad you're here. I'm seeing some friendly faces, so. We're moving on to chapter 10. Do let me know if you have any questions. Chapter 9 stuff. I'll also be here for my office hour after. So this one, so basically, idea is we've studied linear motion, constant velocity, constant acceleration. We also did like 2D motion and projectile motion. We studied objects that are rotating or moving at a constant speed in a circle. So in this chapter, and it kind of moves into chapter 11, which is a bit related, we're talking about a new type of motion in which objects vibrate back and forth. And it's a common kind of motion. Periodic, like even if you think of a pendulum on a grandfather clock, it's just swinging back and forth. That's an example of what the textbook calls vibrational motion. So if it goes really, really fast, you'd say it kind of makes a sound and even like it vibrates or something. So what it means, some part of the system is displaced from equilibrium and allowed to respond to forces that tend to restore equilibrium. So there's lots of examples of vibrational motion in nature. Sloshing of water in a bathtub. You can imagine you kind of move around if you kind of get it going, you can get the water sloshing back and forth in the tub and going out of the tub, which is something my kids discovered sort of at some point while I was not in the room. And I came back and there was water everywhere and they were laughing and laughing. So that's also kind of a resonance idea, is that the water has a tendency to want to slosh at a certain frequency. And if the kids that are in the tub start moving around at that frequency, they can get that thing really sloshing. And I think they talk about this bridge. The soldiers are told to march at a step when they cross a bridge, because you don't want to accidentally be marching at a resonance frequency of the bridge and then get the amplitude of the bridge going. So, swaying of a tall building. When I was doing astronomy on the roof of the McLennan building, there's a 16-inch reflecting telescope up there, and I was looking at bright A stars. And when I was an undergraduate, actually, and what you had to do is when it was really windy, the whole building started swaying with this 1 second period. It was about 1.2 seconds or something. And so what it would do is that your star would get out of alignment and in an alignment. And so it would add this periodicity you'd have to take out of your data for brightness. Pendulum of a grandfather clock. Vocal cords in your larynx. If you go like this, and kind of hum while you're touching your throat, try it. You can feel a vibration. So that's actually what sound is. Sound is coming from vibration. And then that gets transmitted into waves in the air, which then spread out into the air as sound waves. And chapter 11 is all about waves. Okay, so some numbers. Well, you've got period and frequency. The frequency and period of vibrational motion are inversely proportional to each other. The time to complete one full cycle of a vibration is called the period T. Not to be confused with tension, I guess. The frequency F is the number of cycles per second. And so it's F is 1 over T, or T is 1 over F. And it's measured in hertz. So I'll just say that this is sometimes called HZ. It's not really an SI unit, but it's a unit. 1 cycle per second. So let's do top question. This one is pretty straightforward. A pendulum has a frequency of 0.5 hertz. What's its period? Is it A, 2 hertz, B, 2 seconds, C, 0.5 hertz, D, 0.5 seconds, or E? It's a trick question. You can't have less than 1 hertz. 97% vote for 2 seconds. The way it looks is just t is 1 divided by 0.5, which is 2. There's a little video. Sometimes there's these cool little videos they show you, but the simplest vibrational motion is when you have a frictionless surface and a horizontal spring. So one side of the spring is connected to a wall, the other side is connected to the object, and it just oscillates it back and forth. So we see a lot. There's something called the equilibrium position, which is the position at which a vibrating object resides when it's not disturbed. So when resting at this position, then the sum of all the forces is 0. And what you do is that during vibrational motion, there's some kind of restoring force. So if you push the object away from equilibrium, there is a new force, which is proportional to how far it is from equilibrium, and it's directed back towards equilibrium. Okay. So you might as well do the 2 examples that come up a lot that are easy to demo. So one is this pendulum. So right now, if it's not swinging, it's in its equilibrium position. So I can put my finger there. If I kind of displace it, then gravity wants to pull it back towards equilibrium. So there's a force to the right if I leave it here. But if it's displaced to the other side, there's a force to the left. So the gravity force is always towards the equilibrium. So if I let it go, what's weird is that when it gets back to equilibrium, it doesn't stop. It overshoots it because it's got some speed at that point. So it stops accelerating at equilibrium, but it keeps going until there's enough force to reverse its motion. And it's the same thing with this hanging spring. It's right now at its equilibrium position, where there's some upward force from the spring that's equal and opposite to the downward force of gravity. But if I displace it from equilibrium and pull it further down, the spring force increases. So now it's more than gravity, so it's going to go boingy back up. Or if I bring it up, the spring force decreases, and now gravity is more, and it'll fall down. So it's a restoring force again towards, if we put it right here, if that's equilibrium, and I displace it from equilibrium, it wants to oscillate around equilibrium. Make sense? There's a very common kind of motion. It's called simple harmonic motion. Okay. Springing around all over the place there. So there's something called amplitude. We had some vocab on the this morning's thing. Let's just go through a couple quick top hat questions. Here are some data from the tracker software, looking at a hanging mass bouncing up and down. So I've got here x is a vertical distance in centimeters, because there's a little times 10 to the minus 2. And x equals 0 was defined to be the center of vibrational motion. So you may want to think about what that curve kind of looks like if you've ever seen, I don't know, there's trig functions that look a bit like this. But my question is, what's the frequency of this motion? And then I'll ask you about the amplitude for the same exact graph. So frequency is 1 over the period. The period is a little bit bigger than 1 second, so the frequency is a little bit less. It's around 0.8 hertz, I think, for this motion. So good job on that. Next question is exactly the same graph, but what's the amplitude? Well, let's look a little closer at the graph. So this one was 0.8. This is saying it's either 6 centimeters, 12 centimeters, 6 meters, or 12 meters. Again, hopefully you can see it. Well, it's definitely not the meters. So there was a 10 to the minus 2. You might not have seen it, but it's also mentioned here that it's 6 centimeters. so it's not meters. So the answers that I liked were either A or B. So in physics, we have this convention that it's 6. So the range of motion is 2A when you define this amplitude. The reason we do that is so that then we can model this whole thing with a cosine function, which is our sort of strategy here. But I think it can get confusing if you spend a lot of time at sea or something, because I think when people report the size of waves on the ocean, they're actually reporting 2A. They say, oh, the waves are like 5 meters high. Well, they mean from the like the trough to the crest, right? And what we mean in physics is the amplitude A is half the total range of motion. Okay? Any questions about any of that stuff? I don't see any hands. So 6. Call that A. This morning's pre-class quiz was asking about the instantaneous velocity. So if you think about this, this is x versus time, right? Here's time. So the slope of a tangent is the instantaneous velocity. You guys remember that? So the question on this morning's quiz was, at the instant when the object is at its maximum displacement from equilibrium, what is its instantaneous velocity? Well, that would be like here, you'd have a slope. So this is v is equal to 0 right there. So what's weird is that it kind of speeds up, and it's actually going fastest when it's at equilibrium, where there's 0 force, which is, to me, a bit counterintuitive. And then when it gets to its maximum displacement, I feel like that's when the string is, or the spring or something, or whatever force is at its maximum, that's when it's stopped. So everything's a bit wonky here. I guess the force is related to the acceleration, and the velocity is this other thing. So you did that right. At maximum displacement, the instantaneous velocity is 0. There was some just vocab questions. Maximum distance from the equilibrium position is the amplitude. So that's good. And then one cycle is called the period. Okay. So it's easier, I think, sometimes to view this thing from horizontally motion here. A spring with a mass attached to it is stretched and then released. When the spring returns to equilibrium, will the mass be moving? And the answer is yes, because it was pulled there by a force that was always towards the equilibrium. There's nothing slowing it down because it's on a frictionless surface. So when it gets to equilibrium, this is the whole key with simple harmonic motion, inertia carries it past equilibrium to the opposite side. And that's why this whole thing ends up repeating. After passing equilibrium, the acceleration is opposite to the velocity, so it starts slowing down the minute it goes past equilibrium. And then it slows down and eventually turns around. So the way we do the analysis, step 1 is we define x equals 0, the origin, to be the equilibrium. Then we just do the forces. It's Hooke's law. This comes up sometimes in this course, but basically it's F equals negative kx. The negative sign means that the force is opposite the displacement. X is the displacement there. And we also have Newton's second law. We can just combine these two equations. If the net force is Hooke's law, there you go. A equals negative k over m times x. So that's easy. You just say, so what is acceleration, by the way? Acceleration is the rate of change of velocity, and velocity is the rate of change of x. So if you stare at this equation long enough, it gets a little strange. What you're saying is that let's write it out in terms of calculus. What you're saying is that d squared by dt squared of x is equal to negative some constant, k over m, times x. So you've got this is actually a weird second order differential equation of x. The second time derivative of x equals some constant, negative constant times x. This is a weird thing, and it comes up in, so it's not constant acceleration. You can't use any of those equations from chapter 2. It's not going to work. Okay. A is not constant. So forget about equations of constant acceleration. Don't use them when you're doing simple harmonic motion. Because the force is variable, right? And so the acceleration is always changing. So what are you going to do? Well, I remember getting to this point in my math class, because you can, when doing calculus, you can get these equations pretty easily. And what they did is they wrote down this. So I distinctly remember the moment when I was sitting in calculus class and the professor got to this equation where it was a d squared x by dt squared equals negative a constant times x. And then he turned around and he said, and now we will introduce a trial solution. And he turned back and he wrote this equation. And he continued, he did some derivatives of cos, and ended up being a negative cos. There was a 2 pi over t came out twice. There was a 4 pi squared over t squared. Anyway, it all worked out beautifully. So I raised my hand. I said, okay, yeah, but where did you get the trial solution? And he said, it's a trial solution. It works. Look. And that was the end of it. He wasn't going to tell me where the trial solution came from. I still don't know where the trial... Because to me, cosine is adjacent over hypotenuse, which is something to do with a triangle. But if you think of a mass on a spring, where's the triangle? No triangle at all. There's no adjacent or opposite. So what we're doing is we're taking this cosine button on our calculator and just saying, okay, it's a function, right? If I have some angle, like 30 degrees, I press 30 and I press the cos button on my calculator, it gives me a new number. So we're going to do that as now a function, and we're going to say x, the position, is equal to some function of time. And so anytime I want to know where it is, I'm going to pretend that time is an angle of some kind, and then I'm going to type it in my calculator. I'm going to press the cos button, and that'll give me the position. And it works beautifully. So there you go. And I think maybe next class, what time is it now? Yeah, we got it. Now, I think what I'll do next class, I'll bring up a Google sheet, and we'll do an actual numerical integration of this, and you'll see that it really is cos. The other thing is that you could also use a sine function. That also works. That's another trial solution that works. And someone asked this morning, what does the t in this equation represent? So lowercase t is the time in seconds, and the whole idea here is that x is a function of time. The uppercase A and the uppercase T are constants of motion. It's the amplitude and the period. So that's set by the system somehow. It doesn't change. So it looks like this. It's a mathematical model of motion. I will talk more about this model, and I'll kind of try to motivate it with a little numerical integration, which is kind of fun to do on Friday. Keep on going with chapter 10. Here's this graph. You can think about at what point does the object have the greatest speed, greatest magnitude of acceleration, greatest restoring force, and then the least of those things. Have a good one. I'll see you Friday.